I'm going to assume that everyone who's going to be here is going to be here. So, shall we get started? Okay, so it's my pleasure to introduce Rostom Mbarek, who is an expert in high energy emission and plasma properties of black hole coronae and particle acceleration in black hole jets, coronae, and accretion disks. He did his PhD at the Kavli Institute for Cosmological Physics at the University of Chicago, and is currently has a postdoctoral fellowship, a Jerry Side Prize postdoctoral fellowship at the University of Maryland and NASA Goddard. He's working on particle acceleration in AGN jets, and the acceleration, propagation, and deflection of ultra-high energy cosmic rays, alongside understanding the plasma properties of black hole coronae, and also working on neutrinos, reconnection, and turbulence in the context of particle acceleration in AGN jets.
Cool. Thanks, okay, so if everyone can hear me. All right, so I'm going to tell you a story about this diffuse neutrino flux from coronae of supermassive black holes. I know that there are a lot of backgrounds here, people from different fields, etc. So I'll start by describing what diffuse neutrino flux is initially, what I mean by coronae of, and then what I mean by coronae of supermassive black holes. All right, so why is this? Yeah, okay. So for the purposes of this talk, what we care about in terms of neutrinos or neutrino energies is what's in between GeV and tens of PeV in energy, right? GeV is 10 to the 12 electron volts. And this is basically what we refer to as high energy neutrinos. The rest of neutrinos are quite interesting, yes, but they're not relevant for the purposes of this talk, including ultra-high energy neutrinos, which have not been detected yet. So, in this talk, I will be talking about the neutrinos that are in this sort of diffuse signal energy range, and also about this new neutrino flux that we got out of NGC 1068, which is a secret galaxy. That's basically from a single source. So I will start by looking at the single source and then try to go on and think about the diffuse signal based on this single source. So basically that's the gist of this talk. And so this will be based on data from IceCube. And in the next few years, and even now, there are multiple new neutrino detectors that are coming online, already online, like KM3net, which basically will make most of what I'm saying truer or falser. These are words. Okay, and so basically, the IceCube detector is, in a few words, a kilometer square detector under the ice in the South Pole, which is made out of these sort of photomultiplier tubes, you can think of them. And so if you have a neutrino coming in from here or from under the Earth or anywhere, actually, it starts interacting with the ice here through, by interacting through charge current interactions, and then basically that gives you a shower of like electrons or tauons or muons, depending on the lepton flavor of your neutrino initially, and that gets detected afterwards by these photomultipliers through tubes through Cherenkov radiation. So that's basically what is being detected with these neutrinos. So it is quite difficult to make measurements of these neutrino events, and that's why in addition to the fact that neutrinos interact very weakly with anything, that's what makes them great, that's what makes them notoriously hard to detect. And so within what I will be talking about, and some of you might have seen this cartoon before, Great. I haven't said anything for Zoom people since it's done. So yeah. So I will try to convince you that we can use neutrinos to understand coronae and disks of AGMs just based on the arguments that we'll be presenting, which are mostly theoretical, analytical in general. Okay, so this diffuse signal, as I said earlier, is just a bunch of neutrinos that we know are extragalactic in origin because they're coming from not the galactic disk, basically everywhere else. And they are extra hard to detect because you have atmospheric neutrinos that basically dominate and inundate this flux up until this 10-ish TeV sort of level. We don't know much about them, except that they have to be coming from hadronic processes, basically interactions between protons and photons, or interactions between protons and protons, because of the high energies that they show up at. They cannot be leptonic because leptons would cool at much earlier energies for processes that we can discuss. And so what that means is that we need these sort of high energy neutrinos to come from highly magnetized regions, and at the same time, regions that have properties that can give you either proton-proton interactions or proton-photon interactions. If you think about it, sort of in a trivial way, having proton-proton interactions, means that your mean free path for these interactions is quite small, means you need to have a certain large density of protons, which might make your magnetization sort of lower, and so that makes proton acceleration harder. So, intuitively, it's easier to think of photon-meson interactions as the ones to go for, but we still need to think about both. And so if we think about regions that can basically, in AGMs, that can basically give you these sort of phenomena, it's either jets or coronae. Why? Because they're both magnetized, have strong radiation fields, and all of the other arguments that I stated earlier. The nice thing is that over the past 2 years, we got a neutrino signal from a signal source, which is roughly 80-ish neutrinos, which is a great deal. And because that enables us to basically have a sort of slope for the spectrum that we expect. Now, the source, called NGC1068, is a Seyfert galaxy, and it has a quite weak jet. The jet is it's hardly seen. And so that made the corona
sort of well seen, it's just really close. It's intrinsically weak, or they
it's very
well
weak.
mapped out. Yeah.
Yes, absolutely. And so so the corona becomes the most likely neutrino source if you fold in other observables, including the winds that are coming out of NGC1068, which cannot give you, in the most optimistic case, like 10-ish% of the neutrino flux that we see, because this neutrino flux is quite high, quite large, and basically star-forming regions, etc., etc. So basically, the corona has become this sort of source that everyone almost agrees on, that can give you this very large neutrino flux that is associated with NGC1068. Okay, so when I say corona, what do I mean by corona? Because, lots of people sort of disagree on this, considering that it's a very difficult subject to deal with. But what I mean by corona is that it's energetic plasma near the black hole with a morphology that is not well understood. I do not care about the morphology for the purposes of this talk. All I care about is the stuff that we know from X-rays, which are this compact plasma with size roughly 10 Rg within around the energy of the black hole and is the main emitter of X-rays. Lots of people discuss different types of morphologies for the corona, but these are not relevant for the purposes of this talk. All I care about is 10 RG in size and main emitter of X-rays. Okay, so in the first part of the talk, I will be talking about this benchmark case of NGC 1068, and then thinking about it later on in terms of the diffuse flux. So, in order to think about NGC 1068 as a source for neutrinos, we need to understand cooling from proton-proton interactions versus photomeson interactions. Of course, we need to understand for that the photon fields relevant for neutrino emissions if we think about photomeson interactions. Then, importantly, gamma ray suppression, because if you have these hydronic processes, you get twice as many gamma rays as neutrinos when you have one interaction between a proton-photon or proton-proton. And what we see from NGC 1068 is that the gamma ray flux is very weak, very, very weak compared to the neutrino one. Then the magnetic fields, of course, because they're at the heart of particle acceleration. All right, so to summarize the first part of the talk before saying it, basically from energy conservation, we can get a neutrino energy density associated with this corona, where this kappa is a sort of optical depth for neutrino production, which is basically the escape time divided by the cooling time of neutrinos, this thing, whether PP or P gamma. I'll refer to proton-proton as PP and P gamma as photomeson. Then, how do we retrieve this, the slope of the accelerated protons based on the slope of neutrinos that we get out of ice cube? It is based on this particular formula. And so this S here, as I'll refer to it later on, is the slope of the proton spectrum. Q is the one that we get out of ice cube, and it's around 3.2. So from observations. And so T nu is mostly energy independent. That's a weak scaling with E, as I'll argue later. And the escape time also scales weakly with energy. And that is something we can also discuss, but that's also the case here. And so, because protons might be confined in the corona, and so what we end up getting is that this kappa is roughly constant, which means that S is roughly around 3.2, and we know empirically from particle and cell simulations that we can move on from a sigma, which is this magnetization parameter that I'll talk about in a second, to a slope S for the non-thermal tails of these particles that are accelerated. And so what that gives us is that the sigma should be around 1-ish. All right, so this is just the summary of what I'll talk about. So if you're confused, that's good. Hopefully you'll pay more attention to what I'll say. Okay, sorry, I don't know how to. Okay, good. Yeah, all right, so let's start with the observables. So first we have this X-ray emission from NGC 1068. The X-ray emission basically gives us a sort of expected slope for the energy density of X-rays that we have in the corona. This is based on the flux, as they should sort of scale. And the other interesting thing is that we can think about some UVs associated with these X-rays based on type 1 Sieverts, or type 1 AGN in general. So NGC 1068 is a type 2 AGN, which means that we are kind of looking at it edge on. And so what that means is that we can't really see what is happening. However, there's this very interesting relationship that we get mostly out of type 1 AGN that relates the X-ray luminosity to the luminosity at 2500 angstroms, right? And the other interesting thing, which is called the alpha OX relationship. So the other interesting thing is that the half-life radius associated with this 2500 angstrom radiation is mostly, or pretty much at 100 RG from the black hole for a very large range of black hole masses based on microlensing results. So what that means is that if we have the half-life radius of this 2500 angstrom radiation field, we can understand we can get what the energy density of the 2500 angstrom would be in the corona, roughly. That's based on just some simple physics. So now, since we have a better grasp of what kind of photon fields we can think about for sure in this corona, X-rays 2500, let's move on, 2500 angstroms, let's move on to the magnetic fields. All right, so if we want to understand how the magnetic fields work out here, we need to understand how the X-rays are produced. And so if you have magnetic reconnection driving particle acceleration, pair acceleration, which ends up giving you these X-rays, then you expect your magnetic field to be roughly 10 to the 4 Gauss. And that's based on the scaling that the energy density of magnetic fields needs to be with that of the energy density of X-rays. Now, if turbulence is the main driver of this X-ray production, then you end up with a magnetic field that is roughly 10 to the 3 Gauss. That's also based on the same argument. So based on this, on these scalings, we can move on to understand what the electron density in the corona will be like, and the magnetization in the corona would be like, and finally the overall magnetization would be like. So to remind you, the magnetization in general, whatever species we care about, is basically the energy density of magnetic fields, B, which scales with B squared, divided by mn c squared, whatever your density and mass for whatever species we are talking about. So we can describe the pair magnetization in terms of the compactness and the ratio between UB and UX, which are the energy densities of magnetic field and X-rays. And we know from Coronae observations over multiple decades that they should have a tau or optical depth of roughly 1. So that gives us a magnetization in pairs of 10 to 100. Okay? And so then you can get a coronal pair density out of that, which is for NGC 1068. This value doesn't really matter that much, 10 to the 11. Then we can think about the proton magnetization out of that. Why? Because the proton magnetization can be described with this formula, which is basically relating sigma pairs to the density of electrons. And we know that sigma protons, the sigma p, is the one that will be setting the overall sigma if sigma p is less than sigma pairs, just based on this formula. And we also know from what I said earlier that sigma should be roughly 1. So you can make an easy argument that sigma pairs is roughly 1. Sigma, so here what we get out of this is that the overall sigma is roughly 1, sigma pairs is roughly 1, and sigma protons is roughly 1, and sigma pairs is 10ish to 100, depending on whether you think about it in terms of reconnection or turbulence driving what's happening in the corona. So the nice thing is that that can enable us to figure out what the density of protons would be in the corona, just based on this argument, and based on this the description of how sigma pair protons is related to sigma pairs.
On that slide, what's your beta R there in the first relation?
Sorry,
You expose like beta R.
Oh, yeah, I'm sorry. Beta R is just the reconnection rate, 0.1-ish. Yeah. All right, so proton cooling. All right, so here we have to think about whether we want to end up with proton-proton or photomeson interactions. That's the goal of this plot. And based on observables, now we can figure out what photomeson interactions will be like. That's the dark blue line. Now, proton-proton interactions. So, sorry, this is the mean free path for interactions in terms of the size of the corona RC. Okay, so it's just a normalized mean free path for these interactions. And so this lambda pp here is scaled by NP over NE, which is the density of protons and density of pairs. And from what we got in the previous slide, we know that's roughly 100-ish. And E over NP is roughly 100-ish because of that sigma proton argument versus sigma pair argument. What that means is that, this is a normalized plot, is that this one, if we want to compare it to this one, should be up here 100 times more. But I just left it like this because it might help out later with the diffuse argument. The other thing, so what that means is that photomeson wins. So that's the conclusion out of this. Even if you have proton-proton interactions in the corona, photomeson is the one that dominates neutrino production. And one also has to check whether the acceleration time, of course, is less than the cooling time, because you need to accelerate, reach those energies before doing that. And it seems to be the case both for turbulence and reconnection. All right. Now, gamma ray suppression. All right. So this is a quite interesting thing to think about because, as I said earlier, the neutrino flux that we get is quite large, but the gamma ray flux in the same energy bins is almost non-existent. That can be seen in this in these magic limits. Magic is an experiment. No? And so basically, this is what you would expect the gamma ray flux to be a bit above the neutrino one, which is the dotted blue here, but you don't see it at all. These are just limits, as I said earlier. But if you account for the effects of that 2500 angstrom photon fields that I said earlier, through gamma-gamma interactions or Bright-Wheeler interactions, photon-photon interactions, you get to suppress these gamma rays that you've just created. So you create your gamma rays, they just disappear because of the UVs or optical UV 2500 angstrom photons that you have in the corona that we got out of the alpha OX relation earlier on. And so that basically puts your gamma ray flux at least at this level below the magic limits. If you only include the effects of X-rays, you have these dotted lines, dashed lines here. So you do need to have optical UV or something to suppress your gamma rays in the run. All right, okay, so that's still a good story. Now, let's move on to proton acceleration.
They can also cool the gas. So did you check that the inverse Compton cooling is not
This is
reasonable?
based on inverse Compton cooling giving you the X-rays out of the corona.
Okay.
Yeah, this whole story is about bulk condensation. Yes. So if we think about now that we have a more or less self-consistent picture out of this stuff, let's go back to proton acceleration and think about it more thoroughly. So if we have this slope of 3, the observed one is 3.2-ish, and we have a sigma of 1, then we have basically either magnetically dominated turbulence giving you this sort of slope or reconnection. Both of them give similar non-thermal tails. Now let's put that in a sort of plot that enables us to think about CITA 68. All right, let's forget about these blue lines here. So we figured out what the coronal proton density should be like, or the bulk one. We know what the slope should be like, all right? So we put that in there, we put that with pairs and everything. We basically have a flux that's too low if we just go on and increase our energy interval for this non-thermal tail. If we compare it with what we expect from the observations. This is the proton spectrum that we expect out based on our observations. I'm like, okay, now what's happening? So there are two stories here. Either if what I'm saying is correct, what we are saying is that either what we understand of the particle acceleration is not fully correct, or we need another population of protons that is injected into this corona and pre-accelerated to very large sigmas, initial Lorentz factors, which are the sigmas, because that's the initial injection where things are happening. And they have to be injected, why at high sigmas? Because you don't want your density of this injected population to overshoot the overall X-ray energy that you get out of your corona. Why? Because these guys must be magnetically powered at some level. And we already know that the X-rays energy density scales with the magnetic energy density. And so that basically means that we should have something that looks like this if we want to explain the CITA 68 signal out of the corona. So, yeah, but in general, what matters is that the ratio, whether we understand whatever is happening in terms of particle acceleration or not, what matters is that the ratio between this point here and this point here should be roughly 10 to the 5-ish in terms of density ratios. All right, so now let's say that the story that I said about injecting into the corona this other population out of something that is in the vicinity of the corona, does that even work? Because you have to inject and then these have to be reaccelerated and then, So that's what we tried in here using particle and cell simulations. By having a turbulent box and then injecting a population of ions into this box with a certain larger magnetization for this population and seeing how that population evolves in the box. And what we see is that if I inject this dashed black population into my turbulent box, which would have properties similar to what I've been talking about in terms of the corona, then I have reacceleration that ends up having a similar slope to what I have in there, which kind of makes sense. Like you are injecting a non-thermal population into the box, and then this population gets reaccelerated, and then it ends up having similar properties to whatever you have in there. And so I did that with decaying and driven turbulence, and it seems not to care much about it, especially that the acceleration time seems to be quite shorter than the decaying time of my box. All right, and then we have to think about the escape time that I was telling you about earlier. And it seems also to have roughly this sort of energy, very small energy dependence with respect to Larmor radius or energy. And so that is consistent with that story that I was talking about in the summary before. Okay, now that I've told you the story, where are these populations of large sigma, large Lorentz vector protons coming from? Where are they coming from? And like we've come up with some ideas, maybe this asymmetric reconnection that I was talking about earlier, or the black hole rotational equator during magnetic flux eruptions. So basically you have a bunch of bursts that would be injecting protons into your corona, and then this gets reaccelerated afterwards, or at the interface between magnetic loops of alternating polarity. I mean, these are just some ideas, but I'm not sticking with any of them for now. It's just that this is what we know so far, and that's how we can think about it. Now, I have not fully discussed a scenario where magnetic reconnection is the one doing the acceleration. That has very similar problems, and at the same time, if we want to have a corona that is made out of multiple current sheets, then we're back to the turbulence scenario, right? Unless it is one current sheet doing everything, and that's also, I believe, quite a statement, because you need your corona to be a current sheet. And there are some studies that I can point you to that think about this in terms of NGC 1068. All right, so to summarize this first part, the corona has favorable properties for neutrino emission. Photomeson interactions are the dominant ones. Turbulence or reconnection alone in this framework, if we understand fully particle acceleration, and I emphasize that, a combination of both of these guys is needed. Reconnection to inject initially, and then you have reacceleration. And then, again, then there's this injection of proton bursts that could be of interest here. All right, now, can we think about the diffuse signal that I was telling you about earlier to have this diffuse signal?
So can I ask you a question first?
Go ahead.
So 1068 is reasonably nearby. It's like 45.
It's 14-ish megaparsecs.
14 megaparsecs, exactly. Yeah. Circinus is a lot closer, about a factor of 3 closer.
Which one?
Circinus.
Yes.
It's another steeper.
Okay.
It's a little less luminous, but it should be. Flux is roughly the same. So the question is, has it been seen in neutrinos or not?
So it's no, it has. I mean, there are a few.
But it's also got a radio jet.
Yeah,
stronger than 1068.
I see. There are a few new candidates in terms of Sieverts, 4151. If you're NGC,
that's also pretty close.
Yes. And then I forgot the name of the other two, but they have the same significance as NGC 1068 had at 2021, because you have to do like a sort of integration add up, and it's all about the energy density of your X-rays in the corona. So you have to take into consideration the black hole mass, the X-ray density into the mix to understand what the neutrino flux would be like. It's not just, this is just X-rays, or this is, because if you just take in the X-rays, you might overshoot your and as I will discuss a bit here, your overall flux if you want to do some type of integration. So yes, but looking at other Sieverts is something that IceCube people are doing, for sure. All right, so the goal of this part of the talk is to get some type of overall neutrino luminosity that is source independent if it is a Sievert galaxy with a nice corona. And so what we start out with is this sort of neutrino luminosity in general, which is dependent on the kappa parameter, right? Which is escape divided by cooling, the proton energy density, and the size of the corona. Then you extend your energy up to higher energies of tens of TeV, do your integration, and figure out whether that is consistent with your diffuse signal. All right, so first we start with this energy density of injected particles. These are the ones giving you these sort of neutrinos. It's that blue plots that I was showing earlier that are coming from the injected particles. And so what we know from NGC 1068, and this is the assumption in what I'll be saying for the rest of the talk, there's this zeta parameter that I called, which is 10 to the minus 5-ish, which means that the density difference between the bulk protons and whatever would be giving you neutrinos at TeV is roughly 10 to the minus 5, as it is in NGC 1068. This is the assumption, and what I'm saying is that this applies to other galaxies because they should have similar plasma properties. And I can discuss later on, based on very, very new results, why I very firmly believe in this more now. But for now, please take it as a given. And so then we can relate the what we expect the bulk proton density in every corona based on the this UB over UX is generally the same, but based on the sort of compactness that we end up with. So basically, NP is gonna be roughly, which is the density of the thermal bulk protons in the corona, is roughly your energy density of X-rays divided by MPC squared. And so that gives us a generalized proton energy density that is dependent on the X-ray luminosity and that zeta parameter, which is encompassed in here, and the black hole mass, which gives you the size of the corona. So basically, this is a statement about how the energy density in X-rays is important in giving you these neutrinos. And this is basically going back to that zeta thing that I was telling you about, which is encompassed in here again, to make sure that I stated my main assumption here. All right, then we can think about a generalized escape time. We can estimate the escape time based on on this relationship, which comes from recent studies by Lemoine et al. On turbulence, if you're familiar. And so we can relate the Larmor radius here to the magnetic field, which we can also relate to the X-ray luminosity because we know how one is powering the other. So that gives us another generalized escape time, which is related to X-ray luminosity and again, black hole mass, because that gives you the size you care about that.
So what are the units then?
Oh, I'm sorry. This is in seconds, I'm sorry.
Seconds.
Yeah, sorry. Yeah, good point for the future. Anyways, then you have the cooling time out of this. And so basically you can do the same stuff that I just talked about and then have a generalized one depending on whatever luminosity and half-light radius of this region that is doing your illumination, and depending on how far away it is from the corona. This 10 to the 2 is a statement about how it's 100 Rg away, this 2500, for example, but you can add whatever elements you want to have if you understand what the luminosity looks like. And then you can have a cooling time associated with that. More importantly, you need to think about the effects of beta-Heitler interactions. What are these? These are basically interactions between photons and hadrons that basically end up giving you pairs, right? And these have a lower threshold, right? So that might rid you of some of your protons that would be readily available to interact with your photons and give you neutrinos. So you also have to think about that. And so there is a sort of factor that one can calculate depending on the black hole, not black hole, but the Heitler interaction time that basically enables you to suppress whatever protons you have. All right, so then kappa we have to think about, it's in terms of this black hole mass and luminosity for escape and TP gamma, but it's, in order to not have, not to conserve energy, this cannot go beyond 1, because if you have a certain population of protons, the maximum that you can get is that all the protons become neutrinos, right? And so what that means is that you can think about certain populations of black hole masses that are more or less likely to give you certain features or even an effect associated with T escape over T gamma, because all of these blue regions here and some of this red stuff here is going to be capped at 1. And so finally, we end up with a neutrino luminosity function depending on the X-ray luminosity and the black hole mass of any sort of galaxy that is Seyfert-like. And depending on whether your kappa is less than 1 or equal to 1, which is also dependent on black hole mass and X-ray luminosity. So it's, it's also the unit ergs per second. Yeah. And so then what we can do is integrate to be able to get a neutrino diffuse signal. How do we integrate? We need to have the X-ray luminosity function and whatever is related to your X-rays, like your 2500 angstroms, for example, because if you have the X-ray luminosity function, you can have a 2500 angstrom luminosity function and then work with that. But we have to think about a black hole mass, supermassive black hole mass of active galaxies function. And that is a bit more complicated because you cannot really relate the X-ray luminosity directly to the black hole mass because they are constrained and related through the accretion rate. And that guy is a bit more less linear. So it's just like a sort of Gaussian thing. So we can't really relate X-rays to black hole mass of active galaxies. So what I did here is looked at different surveys, either quasar surveys for large redshifts, or the best survey for type 1 AGNs for lower ones, to be able to get a sort of supermassive black hole mass distribution function based on redshift. And that gives me this, which is roughly sort of similar. However, as I showed earlier, with that dependence on kappa, the black hole mass might not be relevant in many parts of this interval, because if kappa is 1, black hole mass disappears. You only care about X-ray luminosity. And so finally, I end up with this plot. This is, I guess, where this diffuse thing is coming from. All right, so forget about the blue one, which is the blue plot, which is the most prominent one. And if I only include the X-ray luminosity function in this business and do the integration, I end up with this orange plot, which is set by S, which is the slope of your proton distribution between 3 and 3.5-ish. And so it's basically more than an order of magnitude less than what the diffuse flux gives me. Now, if I include my 2500 angstrom luminosity function that is based on my X-ray luminosity function and alpha OX relationship, I end up with this greenish one, which starts being consistent with the ice cube flux here. Note that I cannot go beyond this line in Coronae because the acceleration time is larger than your cooling time for the photon fields that would be relevant in this region. And these are limits, these are not data points. We have not detected anything
So your
here.
prediction is that it turns over really
Oh
sharply.
yes, it has to turn over sharply if it's coming from Coronae. Now, let's say that I add an ad hoc photon field to this business here, and I put it here. What is interesting is that this falls into the far UV realm, which is not observable because of the absorption due to the ISM or the galaxy's ISM, that is in there. So we cannot observe stuff that is between like 30-ish EV to like 100-ish EV. And so this is where this effect is here. And so what I did here is had an energy density of these far UVs being at the same level as the energy density of the 2500 angstrom photon fields. Okay, so have that equal to that, and that sort of fits the data in there, all right? And so what I'm saying here is that provided that we know that we fixed the neutrino spectrum at the highest energy levels with the 2500 angstrom relationship, which is this sort of observed, almost assumption-free relationship that basically fits the neutrinos at the highest levels, then whatever affects them at lower energies, including soft X-rays, we can think about in math because of its effects on the corona. So the energy density of whatever photon fields you have has an effect on your corona, right? And then the energy density sets what the effects on the neutrinos looks like. And so we can figure out what the half-life radius of these guys maybe will be, and based on their effects on the neutrinos. And so the interesting thing in here is that if I believe what I just said here, and if you believe it, then it seems like if I have two black bodies for both 2500 angstrom and this far UV, it doesn't work out. And so what that means is that like you need to have the 2500 angstrom temperature equal to the far UV temperature, which is kind of, the statement, right? And so that's not possible. So you need to have some type of non-thermal source that gives you either the 2500 angstrom photon field or the far UV one. Don't read this last sentence. I guess it's just one of the ideas I'm thinking about, but I need a real observer to help me out with this. So for example, here, like if I have helium emission lines, emission lines could do it, I guess, as a non-thermal, like not black body source. They would be obscured, and then they could give you some of these neutrinos. All right.
There's a soft X-ray excess that's sometimes observed.
The soft X-ray excess, unfortunately, fortunately, falls under here, which is dominated by the atmospheric neutrinos. And so it might be possible to, if we know more, we know about soft X-rays, how they look like, right? Because we can observe them. We can use that to help out with figuring out what the level of extragalactic neutrinos would be versus the atmospheric one, but not do it directly.
Can we go back maybe a couple of steps? So you
Yes,
have a high energy proton spectrum,
yes,
which you have some ab initio calculations of. You have some expectation what the distribution of energy is. But that's still somewhat conjectural, I guess. Well, the reason why I ask is that there's this duality between what the proton energy spectrum is and what the energy to see photons you need is, right? In order to fill in the neutrino spectrum. If you change the proton spectrum, you can change the spectrum of the target, or the energy of the target photons, right?
absolutely.
So you feel basically that you have the proton spectrum enough under control that the focus should be on considering different possible target photon populations.
What I'm saying I have under control is that the corona is magnetically dominated, is that the X-rays come from the corona mainly, and that the relationship between the X-rays and 2500 angstroms through this alpha OX are clear. These are the three.
Well, I understand
magnets.
there's a correlation, but there's fuzziness in that correlation.
Oh yeah, because we don't understand the fuzziness. You mean as in like it's not a very clear
You
thing?
showed it, right? There's
Oh,
there's
yes.
a dispersion.
Absolutely, absolutely. This is not about saying that I'm gonna get the exact features of how the spectrum looks like. I'm saying is that if it's within the sigmas, another sigma, within, you know what I mean? Yeah, within the scatter of that, then I should fall at that neutrino energy level if I do a pen and paper calculation. That's what I'm saying.
There are constraints on the harder UV luminosities from line ratios.
Which energy range?
Things to ionize, helium to above 50 eV or whatever.
Yeah, 50 eV is the hard one. You can't really see.
No, you
much.
can't see it, but it affects the ionization state.
Oh yes. There are lots of studies.
Exactly.
And this story that we need to have something in there, that is sort of at the same level is consistent with that. Yes, I haven't put this out yet in a paper because I'm making sure about this relationship. But I think I have a much better argument than what I just said. Much better. Yeah, 0. The talk or the time? That's it. I think these are my summary slides. If you have any questions, please go ahead.
Sure, there are many questions. Right.
So do you have any predictions for what happens if you go, say, to a very high luminosity state, a very, Eddington or even super Eddington, what the implied neutrino flux?
It's the implied neutrino flux will be all about the energy density of the X-rays and whatever comes with it. It's not about the luminosity by itself.
Okay, well, I guess the question really has to do more with your acceleration physics.
Yes.
Does that change at all if you go to very high photon energy density?
If you have a corona that gives you a hard spectrum, like sort of non-thermal tails as we see them in X-rays, then no, because the energy density of magnetic fields will still scale with that of the X-rays. It will keep everything that I've just said the same.
But if you go to a steeper X-ray spectrum,
Steeper X-ray spectrum means that you're not magnetically as dominated, and it might be, like somewhat different, but that means that your X-ray luminosity also decreases, and if your X-ray luminosity decreases, then it decreases your energy density of X-rays, and the same stuff applies.
So did you include that effect when you were doing a summation over
Oh yeah,
black
of
hole
course.
masses?
It's all about the energy density, that Lx over whatever, it's all encompassed in everything.
So I mean, observationally, secrets have a high, UV to X-ray ratio is small compared to in quasars. In quasars, there's fewer X-rays per UV photon.
Yes.
So I'm wondering, was that
Those
included in your
become-
calculation?
Those become a bit more radio loud also, right? So there's a relationship that, you know, connects your X-rays probably to your
Well, the point is that secrets are generally way below Eddington, not always,
yes.
but quasars are almost always near Eddington.
Yes, here your Eddington ratio, I don't care that much about it.
Well, except that it does indicate that you're suppressing the X-rays, right? Right, in the
Suppressing the X-rays. Oh, okay, yes. But
relative
if
to the total accretion rate.
Yeah, I need to see the X-rays to tell the story. I don't, yes, I cannot just say it by looking at other stuff. That's why I would rely on the X-ray luminosity function.
That's what you did.
About you had 3 injector scenarios, asymmetric reconnection, an equatorial current sheet, and interacting loops in the disk.
Yeah.
So if you have the current sheet on the horizon in a thick disk, MAD, it'll be very intermittent, right? It'll only be there once every 2,000 RG over C. So I have 3 related questions. First one is, would that intermittency be enough? Wouldn't you need like a current sheet that was there way more, or well, like constantly?
No, because this is based on like having bursts that are injected and then re-accelerated.
Right.
The fact that they have to be re-accelerated afterwards makes you forget about how often you get injected. And so all you need is to inject enough. It's not about injecting,
Okay.
and not like some time scales that are too large, although that's still fine because it just means that you'd have some type of variability in your neutrino flux coming out, which we cannot think about, considering that we get 79 neutrinos out of this over 10 years. So, yeah.
So for all those 3 scenarios,
Yes.
maybe not the last one, but definitely the first 2,
Yes.
we've seen those in simulations, but then you typically also have a strong jet. I'm not saying it's impossible without a strong jet, but like those scenarios have a really strong jet. So then you would need to think of a different scenario where you wouldn't have a strong jet for this particular case.
Yes. Yeah, I for sure. I have to admit that I don't believe much all 3. And so give me a few months and I'll try to convince you of something else. But yeah.
So, what's a strong jet? So I just go back to the thing about 1068. It's not radio loud in the sense that quasars are radio loud, but there's a definite jet.
Yes.
No question. So, it could be one of these in 1068, the top 2.
Yeah,
There's definitely a jet.
so this asymmetric reconnection we see also in simulations with a weaker jet, or even you see it more prominently in simulations with a weaker jet, so that could maybe be the case. I think the interacting loops with Anya Shashkina's simulations, you also see a weaker jet or a jet that even sometimes breaks up due to the interacting loops. But like the Roberta scenario,
Essentially all secrets have radio jets.
Yes.
So that, I wouldn't rule out the first 2 just on that basis.
No, I agree with you. I guess my main comment is like you have yet another constraint if you take the jet into account and you try to match that with your physical scenario to inject, I guess. But yes, Rostom says yes, potentially better.
No, but it's like I'm trying not to make any conjectures. When it comes to where the source is coming from, just these are possibilities that can give you, this population that is needed at that level. But I'm not saying like I'm gonna go into the details of each one of them. This is for like maybe future studies to think about. It's not a trivial problem.
Okay, thanks. In the interest of time, I think we'll stop the questions there, but please feel free to ask Rostom more questions in the cookie session. You know what happened in the CITA lounge right now, so thank Rostom again. Thank you everyone for being online.
When we say CJets, can you say why? Yeah, I can tell you what. There's a lot of which
Well, even then you need to make choices.